In the last session we discussed Kargar's min-cut algorithm. What is the probability of success? Greater than or equal to 2 by n square, correct? When n is large, this probability is not good. Its probability is small, becoming small. So, the probability of success is not good. So, let us analyze actually the drawbacks or the limitations of that algorithm. Why the probability of success is less? In the last session itself I mentioned the height of the computation tree is order of n. Okay. So, if you can reduce the height of the computation tree and try to increase the probability of success, we can get a better algorithm. So, due to Kargar and Stein in 1996, the improved or the modified min-cut algorithm is proposed. Okay. So, first part is to increase the success probability, that is main focus, and the crucial insight is when you want to reduce the height of the computation tree, you have to increase the number of invocations of the computations of this min-cut algorithm, correct, or the contract part. So, instead of doing actually only one computation in Kargar min-cut will be in a for loop, we can do that one by one we will be doing all the iterations and finishing it off. Okay. Now, you can do 2 iterations there. The algorithm is like this. See, n is the number of vertices in the graph, the input is a graph, correct. What graph, what type of graph? Undirected, unweighted graph. Okay. Then, if the base condition is if n less than or equal to 6, manually or brute force enumeration you can use to compute the min-cut. Okay. Otherwise, suppose n is greater than 6, you use contract algorithm to compute H1, contract algorithm H2, then find recursively this fast min-cut in H1 which is assigned to X1, then compute the fast min-cut recursively and assign that one to X2. Among the two, you can return the smaller one as the min-cut. This is a recursive algorithm. Okay. So, this contract G comma T. Now, the contract algorithm in Kargar's min-cut, what did we do? We contract the edges till the number of vertices is 2, correct. Now, we are not going to reach 2, we will stop that iteration before that itself. While cardinality of the vertex set is greater than T, you pick a random edge and contract that edge. Repeatedly you can contract the edges there, but we are not going to reach n equal to 2 there. When cardinality of T is cardinality of V is greater than T, we will be doing this contraction algorithm. Okay. See, how do you get this base condition? N less than or equal to 6. Okay. Another question is, how do you decide T equal to CL of 1 plus n by root 2? Okay. So, the first one we can discuss now. The second one is given as a tutorial problem. I have given a hint also to complete that problem. Now, the theme of the algorithm is considering 2 instances of contract there and each of size T, then find the min-cut and choose the smaller one. Okay. The recursion is stopped when n less than or equal to 6. Why? When n less than or equal to 6, T is greater than or equal to n. Just you verify that one. What is your T? CL of 1 plus n by root 2. Just substitute some numeric values. When n less than or equal to 6, T is greater than or equal to n. Is it true? When n equal to 4, what is the value of T you are getting? T equal to CL of 1 plus n by root 2. N equal to 4. So, CL of 1 plus 4 by root 2. You are getting T as 4, correct. T equal to n. But when n equal to 1, CL of 1 plus 1 by root 2, what is the value? It is 2, correct, which is greater than n. Up to 6 it is true, correct. But when n is greater than 6, what happens? T will be less than n. Okay. So, when you consider possibility n less than or equal to 6, correct, contracting up to t vertices is not possible, correct. Sometimes t may be greater than, otherwise you have to choose the entire number of vertices and do that one. So, that contract algorithm is not applicable there, correct, since we are imposing the condition while cardinality of V is less than t, you do this one, that is not applicable. That is the reason we choose the base case as n less than or equal to 6. Got the idea? Now, you can draw the computation tree and find the height of the computation tree. You know the algorithm, correct? You want me to project the algorithm? All of you try to draw the computation tree and find the height of the computation tree. It is a binary tree. The root node corresponds to an n node graph, which is your input. The root corresponds to an n vertex graph, then it produces H1, correct, as well as H2, two recursive calls. Then H1, what is the size of the graph or number of vertices? CL of 1 plus n by root 2, correct. So, roughly I can write it as n by root 2 or order of n by root 2. So, similarly here n by root 2. Then H1, again when you pass this one and use the recursive call, you will be having two graphs there. And what about the number of vertices roughly? N by 2, n by 2, like this it proceeds. So, n by 2, n by 2. So, you will be getting a complete binary tree. Okay. You know that the height of a complete binary tree is order of log n, that is correct. Now, how do you estimate the height of this one? When you reduce it by or divide n by 2, you will be normally getting log n to the base 2. Now, I am dividing it by root 2. So, what will be the height of this tree? I will repeat, when you divide n by 2, correct, merge sort for example, you will be dividing the array into two equal parts, correct. N is divided into n by 2 this side and right side n by 2, correct. When you proceed like that, the height of the computation tree is going to be order of log n, okay. Now, it is divided by root 2. So, what will be the height of the computation tree? Log n to the base root 2. This is equal to 2 times log n. So, the height of the computation tree is 2 times log n, which is order of log n. Now, can you find the number of leaves in this computation tree? Very simple. H is the level number there, okay. So, 2 power h, correct. So, if I use that one, number of leaves equal to 2 power 2 log n, which is order of n square, okay. So, the height of the computation tree, see you are able to reduce the height of the computation tree from order of n to order of log n, and the number of leaves in the computation tree is order of n square, okay. Now, what is the advantage of this algorithm? You are able to reduce the height, and in Kargar's min-cut algorithm also it computes order of n square min-cuts there, okay. The leaves correspond to order of n squared min-cuts, and the output is one of the min-cut there, correct. Here also it produces all these leaf nodes computing all the order of n square min-cuts. Output is the smaller one, correct, any one of the correct min-cut. So, what is the advantage of this algorithm over Kargar's min-cut algorithm? In Kargar's min-cut algorithm, the computations are independently done, correct. Computations are not shared. Here the computations are shared, so the computational complexity is going to be reduced, okay. So, let us do the analysis and see. First, see what is the probability of success, correct. We are not very happy with the probability of success of one run of Kargar's min-cut algorithm, that is the reason this improved version. So, algorithm, this fast min cut succeeds in finding a min cut with probability omega of 1 by log n, or it is probability at least 1 by log n. The meaning of that one is at least 1 by log n. Okay. So, we will do the analysis. So, I will assume that C is a min cut. So, let C be a min cut in the graph. I have to find out the success probability. So, I will define, since it is a recursive algorithm, we will define the probability as P of n. Okay. P of n is the probability of producing a correct min cut in the input graph with n nodes. Okay. So, I have to estimate this P of n and show that it is at least 1 by log n. Now, when you consider the graph, that tree computation tree, this is your input graph which corresponds to the root node, then you are having H1 and H2, correct. So, can you write P of n in terms of the probability of success in H1 or in success in H2? P of n is, if the min cut C can survive in H1, that is none of the min cut edges are contracted by the contract algorithm while producing H1, correct. Then we will use this H1 and produce through the proceed through the computation tree, correct, till you get the output. So, probability of, this is one possibility, C survives in H1 and H1 finally produces the correct answer. What is the other possibility? Or C survives in H2 and H2 finally produces the correct answer. Okay. Now, this could be written as probability of C survives in H1. Okay. Now, see, recursively you are doing it. So, you can get a recurrence relation. Now, what about the number of nodes in H1? N by root 2, approximately n by root 2, correct. So, the next step, and H1 finally produces the correct answer. So, can you write it in terms of P? Into P of n is probability of producing the correct answer for an input graph with n vertices. Now, your input is with n by root 2 vertices. So, P of n by root 2, correct, or similarly C survives in H2 into P of similarly n by root 2. Okay. Now, we will first find the probability that C survives in H1. Okay. So, to estimate this probability, you can define some event. Let EI is the event that the ith iteration of contract algorithm does not contract any edge of C. What is probability of C survives in H1 in terms of EI? Probability of, similar to Kargas-Mincut analysis, probability of intersection, that is E1 is even that first iteration is not contracting, correct. So, C survives through all these iterations, okay. So, and C survives the first iteration and in the second iteration and in the third iteration, etc. Intersection I equal to 1 to how many iterations now? Go through the contract algorithm while cardinality of V is less than T. We are starting with n vertices. So, how many iterations? One iteration is actually reducing one vertex. N minus T minus 1. Okay. So, probability of this one. Now, using that Kargas-Mincut analysis, I can write this probability of EI, which is greater than or equal to product I equal to 1 to n minus T minus 1. What is the probability? That analysis, those who remember can tell, n minus I minus 1 by n minus I plus 1. Yes or no? Now, you simplify this one, which is equal to n minus 2 by n into n minus 3 by n minus 1, etc. into T by T plus 1, or what I am getting is n minus T I can cancel. So, plus 1 plus 2 T plus 2. Okay. So, you can cancel many terms, here one term like this. So, what is left out? T minus, the previous term will be T minus 1 into T divided by n into n minus 1. Okay. So, probability of C survives in H1 is greater than or equal to T into T minus 1 by n into n minus 1. Okay. Now, you substitute the value of T there, which is C of 1 plus n by root 2 into C of 1 plus n by root 2 minus 1 divided by n into n minus 1. Now, see, we are going to do some small approximation there, so that easily you can simplify. This is greater than or equal to, I will replace C of 1 plus n by root 2 by n by root 2, correct. So, n by root 2 into this part is n by root 2 minus 1 by n into n minus 1. So, which is n, I will take that 1 by 2 outside, n minus root 2 divided by n into n minus 1. So, which is greater than or equal to half. Okay. The numerator n minus root 2 is greater than n minus 1. So, this will be greater than 1. So, it is greater than or equal to half. Okay. So, similarly, if you do it with H2, are you able to follow? Yes or no? Okay. Thank you. Similarly, probability of C survives in H2 is greater than or equal to half. Okay. Now, see, P of n is written in terms of P of n by root 2, where you are having probability that C survives in H1 as well as RC survives in H2, but C may survive in both in H1 and H2. So, they are not mutually exclusive, they need not be mutually exclusive. So, I cannot make use of the addition theorem there easily. So, you can go for the complementary events. Okay. So, probability of H1 fails to give a correct answer is less than or equal to 1 minus, correct, 1 by 2, this one fails, gives the answer. What I have written is H1 fails to give a correct answer. That means from H1 if you proceed further, you may not be able to get the correct answer. So, that means it is 1 minus this probability into P of n by root 2, okay, 1 by 2 into P of n by root 2. Now, you can write P of n it is, when will the algorithm fail? Both H1 and H2 are not able to succeed in preserving C, correct. So, 1 minus probability of H1 fails and H2 fails. Okay. So, this is equal to 1 minus, see in the previous slide we have done probability of H1 fails to give a correct answer is less than or equal to this one. For H2 also you will be having the same term. Okay. So, this is greater than or equal to, correct, I am writing it as 1 minus 1 by 2 into P of n by root 2 the whole square. Why the whole square? For H1 one term and H2 both fails, correct. Therefore, this is the probability. Okay. So, this is equal to 1 minus, if you simplify, 1 minus 1 by 4 P of n by root 2 the whole square plus, you can cancel, P of n by root 2. Okay. Now, see this recurrence you have to solve. It is not very easy. Here we are going to make a claim. You claim that P of n is greater than or equal to 1 by h, where h is the height of the computation tree. Okay. So, if I substitute it here, P of n is greater than or equal to minus 1 by 4 P of n by root 2. What will be in P of in terms of h, what will be P of n by root 2? This is the height of the computation tree, which is order of log n. Okay. So, at this level you are having n vertices, this level you are having n by root 2 vertices, correct. So, P of n by root 2, if I assume actually the entire thing is happening at this level h, in the previous level you will be having n by root 2 part, correct. So, this one is 1 by 4 into 1 by h minus 1 the whole square plus 1 by h minus 1. Okay. So, again you can make some approximation there. So, it is greater than or equal to 1 by this 1 h into h minus 1 plus 1 by h minus 1. So, you can cancel this one, which is 1 by h. What is your h? 2 log n, height of the computation tree. So, the success probability is at least log n. How many of you are able to appreciate this proof? None of you? See, in the last lecture itself I told you designing randomized algorithm is very easy, correct? It is very simple and easily you can implement also. Only the crucial part is the analysis, probability of success for the Monte Carlo algorithms. Okay. So, now we are able to complete the first result.